today's session on the infrastructure durability and resiliency and policy. We have four speakers today: Dr. Kutay, Dr. Kim, Dr. Kommalapati, and Dr. Demetracopoulou. We will start with Dr. Kutay. He will discuss how climate change affects road maintenance budgets and practices. Then Dr. Kim will cover methods to enhance the durability of stabilized soils for resilient infrastructure under extreme weather. And Dr. Kommalapati will then explore the environmental impacts and life cycle cost of electricity charging and hydrogen refueling stations for advanced vehicles. And last presentation, Dr. Demetracopoulou will focus on integrating equity and justice considerations into transportation asset management. Yesterday, we have what we did in terms of the presentations. We have all four speakers to talk, finish their presentations, and then you write your questions to Q&A. And at the end of all four presentations, we will read those so the presenters can respond to those questions, if that's okay. And we'll start with Dr. Kutay. Dr. Kutay is a professor in the Department of Civil and Environmental Engineering. His specialty is in transportation infrastructure evaluation with a focus on asphalt material characterization, mechanistic empirical pavement design, and preservation techniques. Before he joined to Michigan State, he was at Turner Fairbanks Highway Research Center, and his contributions have earned him numerous awards, including Ashton National Competition Award, ASC Collingwood and Arthur M. Wellington Prizes, and the AAPT Walter J. Emmons Award, as well as the 2023 TRB Best Poster Award. And Dr. Kutay, floor is yours as first speaker.
All right. Thank you so much, Bora, for the great introduction. So I would like to make sure that you see my screen and my pointer. So can you verify
Yes.
here that you can?
Yep.
Okay, awesome. Well, good afternoon, everyone. My name is Emin Kutay, and I'll be presenting our project on the impact of climate change on road maintenance and budget practices. Before I start, I'd like to acknowledge the team and the work. This is definitely a great teamwork. Most of the work has been done by our graduate students, as usual. Dr. Farhad Abdullahi, he just graduated doing his work on this topic, and Tanzila, they are both graduate students, and they worked tirelessly to work on this project. And I'd like to also acknowledge the research team, Dr. Lanutte, Dr. Haider, Dr. Cetin from Michigan State University, and Dr. Zapata and Dr. Uzair from Arizona State University. So here's an outline of today's presentation. I'll start by speaking about the transportation needs being addressed on this particular project. Then I'll continue with key innovations introduced by this research and outcomes, and then I'll end with the deliverable products that we came up with, and then touch base a little bit about the broader impacts of this particular research. Climate change impacts, including rising global temperatures, shifting precipitation patterns, and an increase in frequency of severe weather events, extreme weather events, pose a great challenge for our transportation infrastructure. Among these challenges, the flooding seems to be the most. It stands out as the critical issue. And in this particular project, we have been focusing on the flooding, and there are many other parts, but this is one of the most damaging issues that is that's causing a lot of issues for our pavements. So is flooding a real problem? It is. If you look at the statistics, the flooding, the frequency and intensity of flooding events have been increasing throughout the United States. If you look at this graph right here, there's a significant steady increase, almost exponential at some point for the sea level rise, and also if you look at the high tide, the number of high tide flooding that's happening throughout during the past decade or so, it's been quite high. So this is a major problem, and this problem can cause many issues. It can cause traffic disruptions, road closures, detours. Most importantly, pavement layers can be damaged, and it can also have negative effects on the other sectors of the economy, which heavily relies on transportation. Again, if you look at the statistics, if you look at since 1980s, about more than $1 trillion have been spent to fix the issues related to flooding for the last since 1980s. And if you actually look at this graph, if you look at all the different disasters that has been happening over the years, of course, because of climate change and its effects, there's an exponential increase. But this shaded area, which is flooding, is about more than 60% of all the disasters combined is because of flooding, and then in flood-induced damage. So this is a major issue that needs to be dealt with, and many great researchers have been working on this issue, and then we have been looking at in a certain aspects of this particular problem. Now, if you look at the effects of flooding, flooding or water in the pavement layers can cause damage in many different ways. The most importantly, the unbound layers, the layers below asphalt or concrete, the water content, when it gets to a saturation level, or if it increases, the modulus of elasticity, or we use resilient modulus, decreases because of that, and it reduces the structural support of the unbound layers, and this is very well known. And then this lower structural support causes critical strains, critical responses to increase. And then when these critical responses, such as the strain distribution under a tire, as it increases because of the reduced structural support caused by flooding, the distresses such as rutting, such as cracking, such as roughness, they accelerate, their evolution speed up, and that's a major problem. In addition to the layer properties, there are some indirect effects of the flooding. For example, if a flooded road is, let's say, a high volume road, as shown in here, let's say this highway gets flooded, and then traffic on this highway needs to be detoured. In that case, when you have a detour like this, and then if you have a low volume road that is exposed to traffic, highway traffic that road is not designed for, there is this excessive damage that's happening in that particular road. And even if the traffic, even if the whole area is not fully flooded, there is there's this indirect effect. Also, in addition to this detour effects, and because of flooding, the cleanup or debris trucks, these trucks can be very heavy on the roads, and then these additional traffic caused by the emergency response can cause additional damage, and this can cause significant maintenance costs and then repair costs on the pavement network. Now, as part of this research, the key innovation that was introduced in our research is the development of a mechanistic empirical model to predict the effect of flooding on pavements. So, if you are familiar with Mechanistic Empirical Pavement Design Guide, or MEPDG, or Pavement ME software, it is the state of the art. One of the state-of-the-art methods that are used by agencies to design roads or analyze roads, and there are many other models out there. In our particular in this research, we have a program similar to that and called UpDAPS, and this program has been enhanced to be able to simulate the effect of flooding on the pavement. So this model can consider the climatic effects, air temperature, precipitation, wind speed. All those are input into the model. Material properties, viscoelastic properties, such as dynamic modulus, such as viscoelastic continuum damage theory, constants are entered into the model. Traffic, axle load spectra, class distribution, vehicle class distribution, number of axles, spacing, all that information is input to the model, and the model predicts the mechanistic part of the model predicts the critical strains or stresses depending on the type of the distress, and from these critical distresses, the empirical part of the model produces the actual distresses such as rutting, and cracking. So in this model, in our research, what we did is we made several enhancements so that we can accurately simulate flooding by several means. One of them is decreasing the time step of the simulation so that we can have a daily simulations rather than monthly, which is used in PVAMU. We included nonlinear properties of the base. We included capability of we included a finite element model in addition to layered elastic analysis. We included effects of geogrid reinforcement. So a lot of reinforcement, a lot of improvements have been made to be able to accurately simulate the effects of flooding. One of the issues with such a complicated model is the computational time. Computational time we have resolved this issue by parallelizing the codes and using supercomputers in Argonne National Laboratory, Michigan State University, as well as at the College of Engineering in MSU. We parallelize the code so that a 20-minute or 30-minute simulation can be finished when you run thousands of simulations in only a few seconds when it is run in parallel. Another aspect is because we would like to do this in a network level or in a national level. We've been running the simulations on pavements, literally tens of thousands of pavement sections that are available in the Highway Performance Monitoring System, HPMS, of FHWA. So combining all this information and using big data and the supercomputers, we were able to run many different simulations so that we can analyze the vulnerability of the pavements in different regions in the United States. So in this particular presentation, I'm showing results of about close to 11,000 pavement sections located throughout the United States. This map is showing where each of those pavement sections are located, and we've collected the input data, mechanistic empirical ME input data for all these pavement sections from different sources, some of them from LTPP, some of them from FHWA's default axle load spectra data, and then we perform simulations. And another key component of the simulations is the data about the storm events. So for this, we collected information from NOAA. NOAA has a database for storm events, and there are many records on many different counties. This is actually a plot of the number of flood records in NOAA between 2002 to 2022. We used this data, we extracted this data, and we used the simulations for future simulations based on past flooding that happened in each of these counties, and the roads in each of these counties were exposed to similar flooding events that happened in the past during this period, and then the predictions were performed to simulate the effects of flooding if they exist and if there's no flooding. So there are two ways of using this particular tool. One way you can use at the project level. So if you're interested in a particular pavement section in a county or in a road, and you would like to see if there is a flooding at certain different times throughout its life, what would be the decrease in the life of the pavement. So what you're seeing here is one of the pavement sections in Florida that experienced in its past about 9 major floods and total 54 days of inundation during a typical design life of 20 years. And what you are seeing here is the red line is the simulations with the effect of flooding considered, and blue line not considered. So you can see a very significant jump of rutting that's happening because of the flooding during the flooding times. This is another example for fatigue cracking. Fatigue cracking results for this particular structure, the difference was smaller, but in different areas it could be higher. And what you're seeing here is the IRI, which is the International Roughness Index. And then you can also see an significant effect on the roughness of the pavement. So in order to quantify this effect in the network level, we defined a parameter called resiliency index, simply the time difference between the end of the roughness and the time it takes to get to that end roughness when flooded simulation has been done. So this difference is defined as the number of months or amount of time where the life payment life reduced because of the flooding that's happening. So we call this as resiliency index. If this R is 0, it's fully resilient, meaning flood does not affect the pavement. If as the R goes up, that's the particular pavement that we are analyzing is less resilient as this goes up. So from this, what you are seeing here is we started developing resiliency maps, what we call resiliency maps. So these are all these little dots, and the colors represents the R value reduction in pavement life for each of these pavements that were simulated in HPMS database. This is very useful because if you look at certain zones like this particular county, R values are very high, and is this particular county, R values are very low. So clearly something this county is doing is helping having their roadways resilient against flooding. However, this county, something is going on, something is not going so well. So this is actually very useful for different states, for different counties, to see, to look at their roadway infrastructure and make decisions about what to do to make their pavements more resilient against flooding. So we repeated the simulations for this was for the Gulf of Mexico, and we repeated the simulations for the entire United States on about 10,000 pavements, 11,000 pavements, and you can see the distribution of R values. You can see typical around Florida. In East Coast and West Coast, there are certain areas that are more vulnerable to flooding, and these pavements needs to be perhaps designed and managed in consideration of the flooding that can happen in those. So lastly, this is my last slide. So just to give a brief idea of the broader impacts of our research. I was told not to show any of the equations. I did not show any of the equations. So this is just a general broader impacts. So simply the first and most importantly, it enhances this research, helps enhance the infrastructure resilience by designing resilient road infrastructure capable of withstanding extreme weather events, and hopefully reduce the long-term maintenance. It's a great support for decision makers by looking at these resiliency maps, and then there will be a lot of economic benefits by improving the road durability, by knowing which zones of the pavement in a given county is more vulnerable. There will be less unexpected costs that can happen. And it's a great adaptation strategy to climate change, and it actually supports the sustainable engineering practices of the counties and cities. And it does have a lot of educational and community impact, because these insights gained from this research could be used in universities and new engineers, so that they can design the future pavements and future infrastructure better. With that, that would be the end of my presentation. I'd be happy to answer any questions you might have.
Thank you, Dr. Kutay. Please write your questions to the chat box, and the presenters would respond to them after we finish all the presentations. So thank you, Dr. Kutay. And our next presenter is Dr. Kim. He's a professor and Zachary CV and eminent scholar at Texas A&M University in the Department of Civil and Environmental Engineering. He's a leader in infrastructure materials. His work focuses on the mechanics, characterization, and sustainability of infrastructure systems, with an emphasis on pavements and composite materials. His innovative research integrates experimental mechanics, multi-scale modeling, and advanced material testing to improve infrastructure, resilience, and sustainability. He has authored numerous publications and received extensive research funding from both federal and local agencies, including National Science Foundation, Federal Highway Administration, and Department of DOTs, the Departments of Transportation. And he's recognized as a fellow of the American Society of Civil Engineers and the Engineering Mechanics Institute. And having said that, Dr. Kim, floor is yours. Thank you for presenting today.
Thanks for introduction, Dr. Cetin. Do you see my screen well?
Yes.
Yep.
Okay.
It's good.
Good. So my talk is about durability of soils, considering climate change and extreme weather conditions. And this project is collaboration between Texas A&M TTI and Michigan State University, led by Dr. Bora Cetin. So presentation outline, briefly talk about research team and the overview of this project with some details, innovations, some results, and the work we are working on right now, and the achievements so far, and targeted deliverable and products for end users, and wrapping up with some broader impacts, significance, and conclusions. So as I mentioned, this project is collaboration between TTI, TAMU, and Michigan State. The entire project PI is Dr. Dallas Slater, and myself and Dr. Cetin, co-PIs, and real workhorses are our students and postdoc, Jason, Ayazan, and Kasim. I think they're attending this session, I guess. So Dr. Kutay nicely introduced the issue of climate change. So I don't really repeat again. So with that, challenge, we believe our infrastructure is under, big impact, and particularly stability and longevity are reduced. And most of our infrastructures, like transportation infrastructures, with soils, and we need good soils. So we usually stabilize soils to strengthen and increase the properties. But again, because of the climate change and extreme weather events, our soils are under big challenge. So in this project, we try to enhance the long-term durability of stabilized soils by developing new methods that is very simple and efficient to do it, but with a lot of great science. So we can use the data for better assessing and engineering of stabilized soil for better practice in many transportation infrastructure systems. So this slide shows overall our experimental framework and key innovations. You see, we designed the mix, and then we can assess the durability by conducting two-stage efforts, such as wetting and drying cycles with a very, very small sample, about 1 centimeter by 3 centimeter, 3 to 4 centimeter, for the fine grain soils that can be stabilized. So from this capillary suction type wetting and drying cycles, then accompanied with dynamic mechanical testing and analysis that we developed, we may be able to assess the effect of stabilizers and also effect of durability indicators like wetting and drying cycles for this particular project. So that's our key innovations. I will get some more details in a minute. And number one, number two, the innovations are there. And to make that methodology being developed more viable, we also want to see some other aspects like mechanical strength from typical UCS testing and microstructural analysis using XRM, and also some chemical analysis to understand reactions and kinetics and degradation due to the durability aspect. So the key innovation number one is wetting and drying cycles of stabilized soils. We again make a small sample and put it on porous stone with water infiltrated, and this is very nice way to make a very uniform wetting condition up to about 95-6% saturation. And also after drying, we can control it nicely down to about 50% saturation level. And this wet WD cycle can be repeated, then accompanied by this dynamic mechanical testing, again, the same sample, and then we can assess mechanical properties using the small sample with rheometric analysis. And then this testing is very simple, but it can provide a lot of information of materials. We can see how stiffness degrades, how failure happens, and also how the energy dissipates due to this mechanical loading associated with wet-dry cycle degradation aspect. So we have developed this methodology, and so far we did a lot, and we could see that about 5 samples, a small 5 samples, will be now giving us like a nice level of confidence up to 90% with a good repeatability. If you want a little more accuracy, you need a few more samples, up to 8 samples. But we believe about 5 samples will be enough to get you a pretty good idea of the materials you are dealing with. And also on the right-hand side, after we develop this methodology, we could implement it for different materials, stabilizers, and different types of soils with and without stabilization. And we can get very nice sensitive differences between cases that testing capture with a good repeatability again. So we are very happy with this new methodology under development, and we believe this methodology can get us pretty good idea, differentiating the effect of wetting and drying cycles repeated, for the assessment of durability as part of it. I mean, durability includes a lot of things, but in particularly in this project, we focus on the effect of wetting and drying cycles. So here, just some representative result I can share. We see that with more and more WD cycles, obviously the soil sample degrades, and it gets us property change, like a shear modulus stiffness degraded, and the failure strain also changes with different levels of energy consumption anticipation due to damage accumulated, and the WD cycles obviously affects the material property in the sample. So what I like to say is the methodology is very, very simple, efficient, and cheap and fast, but scientifically rigorous. They give us a lot of good information. So within the year, our students, workforce made a lot of efforts, and we could develop the methodology in a good shape. But we are interested in if the methods we are talking about is actually integrated with other measurement that can give us better different kinds of information, such as bulk level strength, like UCS, and chemistry, QXRD, and also microstructural investigation using X-ray CT machine. So by integrating it all together, we can get better satisfaction, better confidence of the new novel test methods for durability assessment of soils. So this is underway. Second year, we're gonna focus on more of that, and then we try to make the methodology more develop in a better shape and for potentially practical perspective, practical use. So regarding outcomes, we have publication. I mean, the one paper under can impress, and also three nice presentations were made already. And Ayazan, my students, is working on the dissertation, including this type of efforts, DMA, durability aspect of soils with stabilization. So we have already got a lot of outcomes published. So in the end, what we really like to develop, it's very user-friendly, ultimately like specification type test methods, the laboratory testing that can give us scientific information with great efficiency. We try to develop a simple testing, but the scientifically rigorous for the assessment of soils with different additives and the environmental condition associated, how we can make the material for better, in many geotechnical engineering and pavement engineering transportation infrastructure systems. So broad impacts, significance a lot. We try scientific advancement. We never forget practical implementation, practicality for the end users. And ultimately, we develop better infrastructure systems, environmentally beneficial, and economically, the cheap and cost effective. So I think I mentioned pretty much about that. In summary, we are working on new test methods for soil durability with stabilization, and we really appreciate financial supports from Insight and TTI, and also experimental capability in CIR. And I personally congratulate Insight for the very successful anniversary and this great event for the great opportunity for us. Well, thanks for your attention. Again, Professor Little is a PI of this project, and myself and Dr. Cetin, co-PI. So if you have any questions, reach us and we can talk about that. Thank you so much.
Thank you, Dr. Kim. Really appreciate it. Again, feel free to write your questions to Q&A box, and at the end of all presentations, our PIs would respond to your questions. And our next speaker is Professor Kommalapati. Professor Kommalapati has been with pre-review A&M University since 1998, and his expertise includes energy and environmental sustainability, life cycle analysis, air quality modeling, and membrane processes for treating fracking water. He served as Associate Director for Transat Region 6 USDOT UTC from 2017 to 2023. He secured 2 NSF grants totaling $10 million to establish a research center and holds 13 active grants worth over $8.5 million with a career total of $19.7 million. He has published 142 peer-reviewed works and delivered over 210 conference presentations. He has advised 45 plus graduate students, mentored 10 postdocs, and served as a guest editor for 5 journal issues. And he's a professional engineer in Texas, a board certified environmental engineer, and a fellow ASCE. And have a great career, Dr. Kommalapati. Thanks for giving presentation, and floor is yours. Thank you very much for doing this.
Thank you very much. I should have given a little bit shorter bio.
That's what we ask for. Thanks for providing it. So no worries. Thank you.
Thank you very much. Good afternoon, everyone. Today, I would be making a presentation on our Insight project, which is environmental impact and life cycle costs on electricity or electric charging stations to support advanced vehicles. So our project is both charging stations as well as hydrogen fuel stations, but the presentation today is about electric charging stations. My team members, I want to acknowledge my team members here, Mahalakshmi Mannar, who is a staff person working in our center, and Jill Italia is a student, graduate student, who I believe is expected to be presenting some of the work later in this afternoon. We also have a co-PI from Rutgers University, Dr. Yao Wang. I want to thank him as well. So what we plan to present is obviously give you a little bit of introduction, the needs, and then go into the LCA methodology and go over at least some of the sample results, and then end with broader impacts. So as we all know, the transportation sector is one of the sectors that is highly dependent on fossil fuels and heavily contributes towards greenhouse gas emissions. So to address this over the last particularly decade, maybe a couple of decades, but particularly in the last decade or so, we have been looking at alternate sources of energy for this transportation sector in the form of electric vehicles, either battery operated or hybrid vehicles, and also fuel cell vehicles that use hydrogen. So hydrogen is still not taking off at this time, but I can tell you that I am part of another DOE project where we are looking at hydrogen pilot, particularly in major cities, where and how that can be utilized in a way that promotes the use of this hydrogen. But coming back to this one, there are, as of 2023, 3.55 million vehicles, electric vehicles in the United States. A lion's share of them are in California, 1.26 million, and followed by Florida and Texas, about 250K each. And the projections are at least 10% of the new registrations are going to be in this area, new vehicles. So once we are jumping into these, of course, the administration changes and the policy changes may impact that, but so that's something one has to take into account. But adopting these kinds of change in vehicles, change in energy is going to require a significant network of charging stations. Obviously, if you don't have enough charging stations, that discourages people from using these vehicles, and that has been shown time and again that some of the cities, states and cities doesn't have these facilities, don't have that kind of increase in these vehicles. So if we are going to build all these, then obviously we need to have some kind of understanding on the what their environmental impacts are. So here you see the growth of charging ports. Port means one car, that is port, and location is how many stations you have. So as you can see, the graph goes up to 22, but as of 2024, there are 215,000 charging ports and 74,000 locations. So this growth, exponential growth, obviously because of the recent, or not recent, about 2 years ago, we had this law passed, bipartisan law passed, and as a result of that, more and more of these electric charging stations are coming on board. And so it is necessary for us to look at the need for environmental impact, so we can understand what would be the long-term impact of having all these stations. And that's also a way for us to compare apples to apple when we are comparing overall environmental impacts. So this diagram is just a graphic way of showing what I just mentioned. So this is a distribution of charging stations in the United States based on or per state basis, and the darker the color, the more stations you have. And this is how a typical station looks like. And you have slow chargers and fast chargers. Fast chargers take about 20 minutes to 1 hour to go from empty to 80%, versus slow chargers where they may take anywhere between 4 and 10 hours. Okay, so what is it what we are doing? Our approach here is what we call prospective LCA, where by looking at this LCA, one could proactively identify where the problems are. When I say problem, I'm talking about where the maximum emissions are, and then see if we can redesign that process or redesign that phase, or use different forms of energy or different materials so that we can reduce the emissions in that phase. So that is the kind of approach one could take here. And this is highly relevant for built environment and infrastructure related projects. Okay, so here is a methodology. LCA is basically cradle to grave. And what are the different stages? If you take a product, they include material collection, maybe mining. Raw material extraction is done typically using, depending on what material you're talking about, it may be mining. So you take from mining, then process that, transport the materials, and then assemble them or manufacture the parts that you need, assemble them, transport them, and then install them, and finally utilize them. And at the end of the utilization period, then you dispose them off. Every single step in there contributes towards this life cycle impact, environmental impact. So on the left side, you see the process. So for us to do a life cycle analysis, you must identify the boundaries. Before I go for boundaries, you must identify the goal. What is the goal and scope of this analysis? Because that dictates how far we go, what we take into account. Once you have the goal and scope defined, then you look for inventory data, all the data that goes into different parts. Then you do the analysis, and then once you get the assessment done, then what do you do with the numbers? If you sit in front of a computer, it gives you all kinds of data, sometimes way too much data. So how do we utilize that data, interpret that data, and then use it either to improve the product, or to improve or utilize different forms of energy to reduce the total impact, or promote a technology, or in policy decisions, right? So the steps, again, as I mentioned earlier, you need to identify the system boundaries. So here is again a product development, a typical boundaries that you are setting up. So here you have raw material extraction, transportation, manufacturing, again transport the manufactured products into a location where you install them, and then operation and final disposal. Every step we have energy, energy consumption, water consumption. Now, where is the energy coming from? Is it coming from typical grid, or you are using energy from specifically from renewable sources like wind or solar? All that goes into estimating these life cycle impacts. Okay, so we used CIMA Pro 9.6. It's a very well versed system. A lot of folks use it in very high application in Europe particularly. We used LTS 2023 data. Additionally, we reviewed literature and we collected specific data for this project, like materials, production, transportation, etc. So that's what we used in our. Now, when I input this data, the impacts, how do we, as I mentioned, we get a lot of data out of these softwares or these tools. So how do I interpret that data, right? So you can go to the granular level and look at different pollutants that are coming out. But more common one is using these two, what are called midpoint and endpoint categories. Midpoint categories refer to measures that are relatively immediate impact on the environment. Okay, so for example, if you look at the chart there, climate change, ozone depletion, human toxicity, etc. So those are midpoint categories. And endpoint categories are what would be the final impact, right? So for example, what would be the impact of doing something on human health or ecosystem or natural resources, right? Now, if you look at this diagram here, each of those midpoint categories may be contributing to more than one endpoint category. So when we are looking at the data on climate change, then I need to look at, hey, what is the contribution of climate change to human health? What is its contribution to natural environment, or basically biodiversity or ecosystem, that's what they call it, and natural resources. That's how one needs to look at this. So here is, again, I don't want to go into granular level data here. I just want to, this is some of the data that we used. This is just a sample data here, materials and the transportation. Then when we put all this in, we get data. So here I'm showing 10 representations.
Kommalapati, sorry to interrupt. We're coming to the end of the, likely having some time problem. If we can pace it up a little bit, sorry to interrupt.
Okay, so I'll take 2 more minutes. I think I started at 2:15. That's why I'm monitoring the time. But anyway, okay. So
oh, my bad. Sorry about that.
Okay, so midpoint categories here are. I selected 10 of them: climate change, ozone depletion. As you can see, those units are daily. DALY stands for disabled life. The next one is species, how its impact on number of species per year. So as you can see, these are different categories. And now, again, I don't want you to look at all the data or anything, but just want to show you same data, now how it points to different endpoint categories. You can see number 1, global warming, it says human health. Number 2, global warming, how it is affecting terrestrial systems, etc. So I have 4 pages of this, so I don't want to go in. Already I was told about the time. So just to give you an idea. And finally, I want to show you these endpoint categories. So obviously, this is what you want to be looking at. But remember, from when you go from midpoint categories to endpoint category, there is a lot of uncertainty involved in moving from midpoint. You make a lot of assumptions how these factors would impact human health. So there is some uncertainty incorporated into this. But the 3 systems, that is human health, ecosystem, and resources, and then you will see energy, climate change, and water use. So these would be our numbers towards the endpoint, right? So same information that I showed you. So I'll move through slides quickly. This is shown in bar charts. So now you can see which phase is contributing towards this, okay, global warming, which phase. So if you look at that blue, that is coming from the charger. So now you can go into analyze the charger further to see how you can improve or reduce the emissions coming from the charger, like that. Okay, so this is midpoint, and here are the endpoint categories: human health, ecosystem, etc. And same information presented in a bar chart. All right, so this is cost analysis. I'll skip over them. And so as we can see from there, there is a lot of information out there that comes out of these tools, and the important thing is how we interpret this, and that's what we are working on right now. So we are also working on hydrogen fueling stations. So eventually we want to have gas station, electric charging station, and hydrogen fuel station that we want to compare. Okay, so all right, so this obviously this work is contributing towards sustainable development of future infrastructure, which is obviously the goal. And so we're supporting undergraduate and graduate students and a female staff person, and we are publishing this work. We haven't published any yet, but we will be publishing. We presented our work in a couple of locations already. So that is what I have, and I will stop. And I did take only 14 minutes, Dr. Cetin.
Yes, sorry, Dr. Kommalapati. I should have timed it. My bad. I should have timed it. I apologize for
No
it.
problem, no problem.
Thank you very much again. Just write down the questions to Q&A. And we have one more speaker, Dr. Demetracopoulou. I hope I'm saying it right.
Yes,
Vassilina?
that's close enough. Yeah, Demetracopoulou.
Okay, thank you.
Thank you.
And do you mind if I introduce you quickly?
Of course, go ahead.
Okay, thank you again. And Dr. Demetracopoulou, yes, so sorry, is an assistant professor in the Department of Civil and Environmental Engineering at Rutgers University. Her research focuses on project delivery, risk management, and strategic decision-making for infrastructure projects. And she holds a professional engineer's license in Greece. And currently she's working on identifying delivery challenges of infrastructure projects related to interdependencies among different systems, social, environmental, financial, including, and leading research aiming to incorporate equity metrics into transportation asset management, funded by the National Center for Infrastructure Transformation (NCITE), and research on design, build, operate, maintain as a viable delivery model for transit projects funded by New Jersey Transit. And the floor is yours.
Thank you, Bora. Hi, everyone. I'm Vassiliki Demetracopoulou again. Really glad to be here. My presentation doesn't have a lot of technical aspects, as it's an overview of our project, so I'm going to jump through it. First, wait, can you see my screen changing?
No, we see the main slide. Once you move, yep, now it moves.
Okay, that's good. So again, just recognizing our consortium partners. Thank you to INSIDE for the funding and for hosting this event. And quick acknowledgements to our team members. So again, that's the name of the project, the duration, and the PI, the firm Rutgers. There's also Dr. Maher. We have Gabriella from TTI and a team of academics from Prairie View, Dr. Perkins, Dr. Duan, and Dr. Zhang. We have two amazing graduate students, Archie from Rutgers and Valentina from Prairie View A&M. Archie is doing her master's and Valentina her PhD, and they're providing key support for the project. So what is the main motivation? in the title, but what is really, really key to motivate this work is that first, as we define social equity, right, the distribution of impacts, both benefits and cost, to the degree that is considered fair and appropriate. What is the key here? That equality is not equity. So when we talk about decisions, right, that transportation agencies make on funding, design alternatives, asset management, they do really impact the socioeconomic landscape. And the same decision may impact a vulnerable community somewhat different from a less vulnerable community, both on the timing, right? The timing of maintenance of a specific asset that comes into play. What are maybe some of the other indirect consequences of a design alternative, like adding or circumventing a specific vulnerable area through a highway, right? So a lot of these decisions are really hard to track, hard to quantify, and therefore hard to make changes based on data. So here's the gap that this study is trying to fulfill, is to understand that there is a gap in operationalizing the role of social equity in making a lot of these decisions, and particularly to make this decision data-driven by equity data. That is a very clear need that's also recognized by the US DOT Equity Action Plan, released in 2023, that really highlights the need to advance equity through inclusive transportation investments, and particularly the data-driven aspects, and how do we include that in our decisions. So for this particular project, we center around the application of transportation asset management. So in the previous slide, I showed an example of several decisions, but here we're focusing on this transportation asset management, meaning the systems that allow State Department of Transportation, so state DOTs, to develop a systematic process for operating, maintaining, and expanding physical assets effectively throughout their life cycle. Even in an earlier presentation, Dr. Kutay showed some data from the pavement management system, right? And similar to this, a pavement is an asset class. So that's why there are multiple TAM systems within its DOT, but all of them are kind of dictated, or the decisions around it are made by these two key elements: available funding and technical performance. So what do we mean? The decisions on how we manage, we maintain, when do we maintain, and if it's going to be a minor or major rehabilitation, is judged by technical performance. The IRI index, like Dr. Kutay showed in New Jersey, for instance, they use a combination of IRI and SDI. But there's going to be some technical metric to judge the performance and how we maintain assets. These decisions need to be optimized. So how do we make our network within the state, right, our asset class that as we as an owner, as a DOT operate, how do we make that the best we can within constraints from available funding? And what we are trying to develop now is a framework that centers on data, on how do we include social equity impacts to balance in the decision with the technical performance and available funding. So that is basically the key question we're trying to address. How can equity be effectively integrated into our TAM processes? Now, with the transportation needs that are being addressed at the higher level, they align very, very closely with some of the research pillars of the Insight Center. So first, on infrastructure durability and resilience, with our goal here to provide a methodology for integrating equity in TAM system, really can help in ensuring that assets, particularly in vulnerable areas, are adequately maintained and increasingly resilient. And again, that shouldn't be on the expense of assets in different areas, but there is a way to balance this when we make decisions, so that overall network performance remains at our highest possible condition, while we also consider some thresholds for vulnerable areas. In terms of policy, a key element is understanding the misalignment between policy and implementation, particularly as we collect now input from experts across different DOTs. We see a lot of discrepancies around how different tools are being utilized, and how can we provide efficient recommendations in terms of people, process, technology, to make a lot of the existing policies be more efficiently utilized, but also how can we inform future policymaking. So continuing into what are our key innovations for this project. I'm going to guide you first to the pictures on the right. So I talked a little bit already about the USDOT Equity Action Plan. That Equity Action Plan also outlines 5 key pillars. Those 5 pillars are wealth creation, power of community, proactive intervention, planning and capacity building, and expanding access and institutionalizing equity. Now, this is a really, really cohesive way of organizing a lot of how we can develop our metrics, our challenges and barriers, and how to develop recommendation based on each of these pillars. So one of our key when we set out to make our methodology and what is going to be new about this work is that we want to include and not reinvent the wheel, but include federal mandates that are well understood and are easy then for DOTs to incorporate into their actual decision making and practices. So our first kind of federal initiative we tried to do, and as I'll explain later, is use those pillars to organize a lot of the data we collected. The second is using an equity metric that's well understood and vetted, again, by federal initiatives. So in 2023, the USDOT released the ETC Explorer, the USDOT Equitable Transportation Community Explorer. Now, this provides a depth of information around vulnerable communities around the US. They're organized by state and percentiles, and very uniquely to other vulnerability indicators, they do place emphasis also and include transportation insecurity and vulnerability as part of the overall metric. So I'm not going to go again too deep into the methodology that's employed by ETC Explorer, but the final metric comes up from 5 categories on social, environmental, health vulnerability, resiliency, and transportation insecurity. So therefore, what we're using in this study to quantify our equity metric is in parallel to what federal agencies have released and vetted. So that was my second bullet point, right? So one of our key innovation is utilizing in our novel methodology federal initiatives to increase the adoption of the project's result. But the key element here is that our goal is to provide a novel framework and recommendations for integrating that equity data into TAM. And the way we're going to showcase the methodology includes both qualitative data. So I've included a number of, through a stakeholder committee meetings that we performed and a survey that we have released, and quantitative data. So we're using a case study for New Jersey pavement asset class to showcase how our framework would work. So seeing some of these again in a very brief snapshot, some of our project outcomes to date. The first, again, extensive literature review on equity metrics, programs, and applications for transportation owners. That work was particularly supported by our graduate student, Valentina. Gabriella from TTI was instrumental in understanding applications from different transportation owners and across other sectors. What can we learn from other federal or private sectors that are using equity in different decisions? Now, the second here, a second outcome to date, identifying 20 pertinent challenges for integrating equity in TAM decisions through a stakeholder committee comprised of 7 members with diverse backgrounds. So in that specific topic of identifying challenges, so what really prohibits us from making that a standard practice, right? For having equity as part of our decision making. This is a work that my student Archie is going to present a little bit in the later session on students, but also is something that we're working on a conference paper right now. It uses qualitative data and analysis from that stakeholder committee that we did over the spring of last year. And you can see on the right here, a quick snapshot of all the 20 challenges we identified through inductive coding and categorized by the USDOT equity pillars to, again, help in institutionalizing and understanding those results. Now, the third element, developing a survey aiming to understand diverse perspectives on equity across US DOTs. Now, of course, you can see here with our QR code, feel free to use that to browse or even take the survey if you have relevant expertise on equity practices. We have tied those to specific US DOTs because we think it's going to be critical then for reporting purposes to understand what is the different terminologies, for example, training, what are data, what are different tools that agencies utilized in terms of equity metrics across different levels of the project lifecycle. So a lot of the elements we're trying to understand here are really a gap in existing practices, and we hope to shed some light on that and help us interpret some of our results on our quantitative part of the work. And finally, what I discussed previously briefly, examining through the New Jersey condition pavement data to showcase TAM systems with equity considerations. Now, this is an ongoing effort. New Jersey DOT has provided all of their current equity scoring for the state of New Jersey. This was a great contribution to this work, to be used, of course, for these research purposes. So we hope that this is going to provide a really good insight when we present that as a final element to this framework. Finally, the deliverables to stakeholders. Hopefully some of the innovations and some of the discussions I already presented show some of the theoretical contributions, but practically, of course, part of this project is going to be a report that's going to synthesize a lot of our results, literature, the challenges, all the survey we collect across the US DOT states, and what are targeted recommendations we can give for this area. You can see a draft outline of our synthesis report on the right. Of course, that's a really, really draft outline, so it's an ongoing effort. We hope through that, of course, we highlight some specific contributions through papers, conference papers, and journal papers that are all the PIs in the team and our graduate students are working on. Our, again, key theoretical contribution through this work is going to be our novel framework that's going to be supported by quantitative and qualitative case examples, and it's going to utilize federal initiatives that haven't been studied in existing studies in this area. So who are the stakeholders and these end users? Primarily, transportation agency personnel, so experts from state DOTs, from the transportation asset management systems, looking to make these changes and actually incorporating practically equity into their decision making. Of course, policymakers, other transportation users, other agencies, or even end user of the transportation may benefit by understanding what are the potential impacts or discrepancies with existing vulnerability among different states. So that kind of brings back to our contributions and broader impacts. So again, I want to guide you first to the image here on the right. Again, this is a snapshot of our modeling of our, as you can see on the network, you can see the different pavement conditions for New Jersey. The pavements are categorized in poor, fair, and good conditions, and that's color-coded. Particularly the red, poor conditions, and green, good conditions can be easily highlighted within this picture. The other one is the Disadvantaged Community Index that we use, of course, as part of the, as I said, with the ETC Explorer. So that's the composite index that you can see. We categorize based on, we color-coded based on significance. So the higher the index, the more vulnerable the community. And I think that showcases with the circles. So for example, something that visually has a lot more power than showing, statistical correlations perhaps between pavement and vulnerability. You can see with the red circle here, in this area, a lot of vulnerable populations, and red is primarily the condition scores throughout the network in this area. While on the contrary, you can see some of the green areas here, a lot of the green circles that highlight that there are really good conditions for less vulnerable areas. Now, of course, this is not anywhere you can see, this is not everywhere the case. There's a lot of diversity and discrepancy between that, but it's important to understand how pertinent that is within the existing data and how our methodology can help. So we're going to run the same kind of maintenance and optimization algorithm with and without equity to see how potential impacts can be distributed. Also on the bottom, you can see here some of the sections of the road that we have been given by New Jersey DOT. What are some of the categorization of pavement type, is asphalt, composite overlay, or concrete, and what percentage of these, what counts of these sections were categorized as good, fair, or poor condition scores. So ultimately, what we're trying to achieve with this use case is understanding the impact of including equity into TAMU processes and minimizing the gap in asset performance in disadvantaged and non-disadvantaged areas. Again, I ran through as quickly as I could given the time constraints. Thank you for attending this session. And of course, feel free to reach out to me with any questions about the project or anything else. Thank you.
Thank you, Vasilina. Thank you all again. And we have quite a bit questions. The first question is to Dr. Kutay. It asks, does the program provide resilient modulus changes over time to help estimate routing, cracking, and other payment distresses?
Yeah, that's a great question. So it depends on the part of the program that's used. So the pure flooding, UpDAP's flooding program, during the flood event, when there's an event, there's the inundation period and there's the recovery period. So during the inundation period, a reduction factor is used based on literature and the testing that has been done in the past. So resilient modulus during the inundation kind of reduces by a factor, which is an input to for each pavement, and then after the inundation, let's say there's one day, a couple of days, there's a recovery period. During the recovery, the different equations are used to gradually increase the resilient modulus back into the original. So there is a short answer is yes, it does do calculations, but it doesn't do, if the question is about, well, is it based on moisture profile and is predicting the resilient modulus for moisture profile, it is not doing that. That part of the code. It's based on an input, so user inputs that part.
Right. Thank you, Dr. Kutay. And there were LCA-related questions for Dr. Kommalapati.
Dr. Cetin, I tried to respond to that in the chat itself.
Okay.
I think the 3 comments and then below that are my responses, and I hope Abhijit is here to see those responses.
Okay. Thank you. Thank you all for doing this and for all your hard work, and the participants, thanks for being here too. Sorry, it takes it time. I apologize, Professor Kommalapati. I should have
No
time
problem. No
together.
problem.
It's actually,
I randomly pick on you. Sorry about that. So,
I think I might be the main blame on that. It took more time at the beginning, so sorry about that.
Yeah, no worries. Sorry about that. But thanks all. Haley, do we need to do anything else or?
That's it. Thank you all so much. And if we could just